Our next speaker is Peter Burt, who will talk about early ideas in pyramid image processing and relevance today.
All right. You hear me? Is this working? Does this work? How do you use this thing? Whew. All right. Point with the cursor. Point with the cursor. Ah, maybe we would have. Huh. I got a point. All right. All right. Well, let me say it's a great honor for me to be here for Ted Adelson's event. He was a very important element of my career, early career and whole career. And also, I'm very honored to be with this large crowd of such creative people. So that's great. I'm going to talk about work that Ted and I did in the area of pyramid image processing. It's early on stuff. Field has moved on, and maybe people don't know about this stuff anymore. But point particularly to work in image compression, applications to compression, image blending, and image fusion. Now, do I know how to get this thing to work? First a little picture of when in time this was. It was like 40 years ago. And I don't know whether I can get this thing to work. Whoops. I did the wrong thing there. I have to go back. You can see that I'm a little old school and fumble around. Anyway, what I wanted to point out is Ted and I met roughly in 1980. He had just finished his degree, University of Michigan, and gone on to NYU. We've been introduced. And from there, he went to RCA, which became SRI Research Lab. I had gone to University of Massachusetts, then also been at NYU for a postdoc, Bell Labs, and then Rosenfeld at University of Maryland. And it was when I was at University of Maryland, and Ted was just starting, I think, at NYU, that we met at a conference. I was deeply involved in pyramid image processing thinking. Ted was involved thinking about image compression, I think, in the context of multi-resolution domain. But anyway, that's where we met. And then we collaborated. The things I'll talk about were kind of over the next 5 years. First, let me just say a little bit about what a Laplacian pyramid is. That's what this is going to be about. It's long, long ago. Probably don't recall what this is. But basically, I wanted to point out the pyramid is constructed from an original image through a sequence of filtering and downsampling. And that just basically gets it a blurrier and blurrier image. And then, as suggested here, the Gaussian pyramid is on the top. If you expand each layer and subtract it from the previous one, what you get is the difference, or kind of the structural elements at that scale. But what I really wanted to point to is over on the right from your perspective, and my perspective actually, are the sampling functions associated with those pyramids. And so the Gaussian pyramid is basically a Gaussian. Each sample is a weighted average of the original image with a Gaussian weighting function. And it gets larger, twice as large at each successive level. But the Laplacian is basically the difference of two Gaussians. That difference scale by 2. And that's, as shown on the bottom, what were referred to in those days as difference of Gaussian or dogs. So that's kind of what a pyramid is. Where did this idea of a Laplacian pyramid come from? And it actually, for me, started in, I think, high school with this visual illusion that I've got shown here. I got this picture from the internet. That's not my picture. But I think people will be familiar with it. If you hold your fingers up like this, kind of verge your eyes a little bit beyond your fingers, you see what looks like a little hot dog there, or a Frankfurter. And that got me to thinking that, gee, there's something curious going on here. It says something about how the brain must be putting together images from the two eyes. Obviously, there's stereo depth perception, but there's also a kind of a unified image that's being assembled. And what this suggested is that unified image somehow was favoring edge-like structure. So if one eye was seeing at a given direction an edge, and the other was seeing a uniform region, the brain would say, I'm going to go with the edge, and assemble those. So that was this kind of notion of selection and edge-based selection. And then when I went to graduate school, UMass, and it was cybernetics, started getting introduced to neurophysiology and visual neurons in the visual system. There was this notion of cells that have kind of dog, that is difference of Gaussian receptive fields. And not only that, but they came in different sizes. So this is kind of very naive, but I thought, well, gee, if I could construct a way of representing images in terms of difference of Gaussian, and had that constructed so that you had different scales, then maybe I could simulate this binocular fusion thing. But anyway, that's what led to the Laplacian pyramid. Well, that was kind of a notional thing. When Ted and I met, it was the Laplacian pyramid. I was kind of working on that. But what I think Ted and our collaboration led to is some practical applications of this pyramid structure. And the first one is image compression, then multi-resolution blending, and then fusion. And I'm just going to kind of give an example of each of those and try to make the point that, oh, yes, these are still relevant ideas, but I'm not going to make a very strong case for that. All right, compression. So as I mentioned, it was something that I think Ted was already thinking about, working on how to do image compression in a kind of a hierarchical multi-resolution framework. I had this Laplacian pyramid framework, so we tried it out. And we wrote a paper and so on. And basically the idea, the motivation, I guess, is if you have an image and neighboring pixels are highly correlated, if you can kind of subtract the local average, you reduce the variance and you just get the difference, and that can be compressed much more easily. So is it still relevant today? Well, I would say Laplacian pyramid compression is not really used. But I'd like to say maybe it was the forerunner of wavelet compression. Wavelet compression is, the Laplacian pyramid is overcomplete. It has more samples than the original image. Wavelet is just complete. So it's a little bit more efficient. I think Laplacian is better, but wavelet is actually with us today. So for example, it's the coding method used in JPEG 2000, which is digital cinema transmission. So there is some residual, I think, effect. The next application is image blending, multi-resolution image blending, which is to say, suppose you have two images, you want to put them together side by side and blend them smoothly. And the picture here is what we call the ORPL, orange and apple, which appeared on the cover of ACM Transactions on Graphics. But the basic, all right. The basic idea is that rather than blend in the image domain, you make a multi-resolution representation and blend each level at that level, which means you get a very broad blend of low frequencies or a core structure, very narrow blend of high frequencies. And the unique feature is if you have a broad blend, details that are not lined up don't show up as a double image. They're just blended over a very short distance. Well, a recent example, I just tried this out. Suppose we blend these two pictures using the mass structure on the right there. There's the overlay, and there's the blend. And the point I want to make here, I think it's pretty striking. The skin tone blends very smoothly basically over the whole face. But there's no local double imaging features. But I'm going to move on here. I want to say something about fusion. Obviously, fusion was where this all started from. We went stereo binocular fusion. And the idea for fusion was we make a Laplacian pyramid for each of the source images. Then we construct from that a Laplacian pyramid for the fused image by selection. That is, at each sample position, we look at the source, which has the highest local contrast or CLNs or something like that, and just copy it over, then invert the pyramid. So this has been used I don't think we have a good paper on this, but it's been used very extensively. Exposure fusion, which is HDR, focus fusion, I'll give you an example, and then multispectral fusion, which is to say sensors, IR, visible, used very much in the night vision world, for example. But here's one of those examples. This is focus fusion. We have source images. Ted actually has a patent on this. Congratulations. And 3 images with different focus, and go through this process, just selection, invert the pyramid, and you get an image that everything's in focus. Very simple process, and wow, all in focus. Well, having said that, something I just thought of recently in putting this talk together, well, maybe if I go back to that hot dog illusion, what happens if we do that same fusion process? And this is what I get. So I'd say, in a way, it's okay. You see the little hot dog, but you also see a lot more structure around it, which seems to be suppressed in the case of human perception. So this is not a perfect model, but starting point. Finally, here's a image blending example. It's something I found on the internet, and it's on this place called Alex Weblog, and he took Ted and my pictures and lined them up and blended them together, and it works pretty well. So I'd like to say thank you, Ted. I think we got a good start, and we blended this perfectly. So thank you.
Any questions? Yes, Bernd.
I guess it's a question, Peter, to both you and to Ted. Ted, I remember when we worked in the same building, you had a little excerpt of the reviewers' comments on the first submission of your famous Laplacian pyramid paper. And you know, I've been mentioning this to students over the years. I don't quite recall what it said, but maybe you can share that with the audience, you know, for history and for good laughs.
In my closing remarks, I will show you a photo of that review, but the critical line is, I doubt that anyone will ever use this algorithm again.
Fredo.
As many of you know, I work on computational photography, and I just want to highlight how central Laplacian pyramids are still to the field. I mean, whenever people blend panoramas, the leading technique is still pyramid blending, or at least a two-scale version. I'm told that in industry, a lot of the denoising is still done with Laplacian pyramids or wavelets, because people find it a lot more controllable than alternatives. I know Adobe products, Photoshop, Lightroom, when you do any tone mapping and management of highlights and shadows, that's based on local Laplacian filtering, which is an extension that Sylvain Paris developed on top of Laplacian pyramids. So the tool is really still absolutely fundamental in the field.
Well, thank you for pointing that out. I mean, this, the blending and the multifocus are absolutely universally used in your camera, but I'm not quite sure exactly the methods currently used. So I'm interested to see that some of those are still pyramid-based, and I know some of you have worked in this field, so looking forward to learning more.
Okay, thank you very much, Peter. And our next speaker is Eero Simoncelli, who will talk about a new era of image priors.